Hi everyone! After introducing a time aspect to games, now we are going to go over the case where games are played repetitively. For instance, that could be simultaneous moves games played a couple times, but we will also go through the case where they are played infinitely many times. In this case, again, strategies will depend on the history of previous moves. First, the usual disclaimer. I do not legally allow this content to be published without my consent. If I see this content uploaded online, I will take it down and I will report whoever uploaded it. So, if a game is played repeatedly, players may behave differently than if the game is played only once. Think about something like cleaning a shared apartment. If it's only a one-time thing, you might not be very thorough, or you might decide not to do it, or to free ride. But if you have to do it repeatedly, maybe every week or every month for an extended period of time, then based on what was done before, there are going to be some consequences. A repeated game is a given stage game repeated several times. The stage game could be simultaneous or sequential, but one game is called the stage game. It could be played finitely many times. In this case, the game has a fixed length. Let's say you play the game every month for 2 years, so you play it 24 times, or you play it every year for 10 years, and so on. Or the game could be played infinitely many times or an unknown number of times. So there is no predetermined length. We call these games super games. Many games are super games. When you think about it, think about the industries, think about big firms. Some firms are pretty much immortal at this stage. Well, it is impossible for me to say that they are immortal because I don't know what's happening in the future, but think about firms as big as Nike, Coca-Cola, Amazon, Google. Those firms don't seem to be, they don't do bad, and since they are dominant on their respective markets, there are very low chances that another company is going to buy them over and maybe change the name and so on. So firms competing with each other could happen over a non-predetermined length, like period of time. But if you think about Pepsi-Cola and Coca-Cola, chances are they're going to compete, maybe not forever, but this competition is not going to start anytime soon. Or think about customers and firms in general. As long as we live in a market economy, there will always be interactions between customers and firms. So, as long as market economies survive, then these interactions will be repeated. But that could also be interactions in the workplace and the private sphere. We went over smaller scale games, in particular in the public good lecture, and in the applications of the Nash equilibrium concept, where we looked at contributions to a public good, participation to a project, or firms competing with each other, and so on, like duopolies. So that could be interaction with coworkers, with family members, with friends, with maybe managers or CEOs, and so on. Now, how can we distinguish a game tree where moves are simultaneous versus sequential? We use what we call information sets. So, an information set is a very important notion to understand, and this is going to have a crucial impact on how we write strategies. So, an information set is a set of nodes. So, when you think about a tree, think about circling nodes. That would be an information set. But an information set is a set of nodes with a particular features. every node in the set belongs to one player. So I cannot include in my information set the node where one player moves and the node where another player moves. An information set is supposed to describe the information known when a move has to be made. So, two different players nodes cannot be in the same information set because the information will not be the same for each. And when a player is in an information set, he cannot distinguish which node of the set he is at. So if an information set contains 3 nodes, he doesn't know if he is in the left node, middle node, or right node. This means that he doesn't know what happened before. He only knows that it is his turn to play, but he doesn't know what was played before. So this will change the structure of strategies. If we don't know what happened before, then strategies cannot be contingent on each possible history. Well, in this case, there will be only one history. Something was played, but I don't know what. So I only have 2 or 3 options. This action, or that action. If we have multiple histories, then we would be thinking about what to do if this happened, what to do if that happened, what to do if that happened, and so on. By now you should be familiar with our favorite Battle of the Sexes game, played sequentially. Here, each node where Tom is, so this node and that node, are information sets on their own. What that means is that in this information set, there is only one node. So Tom knows that beaucoup was played before. He knows where he's at. In this information set, Tom knows that Rosia went to small victory in the first place. This is a case where the game has perfect information. Whenever something is being played, it is observed by all the other players. Here, Tom observes what Rosia did because he gets a text message. Now imagine the same game, still play sequentially, but Tom doesn't know what Rosia did. So he doesn't get a text message, but he knows that Rosia is somewhere. She's already waiting at a cafe. Which one? He doesn't know. In this case, he knows that it is his turn to move. However, he doesn't know if he is at this node or at that node. And this is why both of these nodes are in the same information set. This means that between these two nodes, he has the same information, which is pretty much nothing. The information is Rosia either went to beaucoup or small victory, but Tom doesn't know which one she went to. Battery died. No text message. So now, he cannot make strategies depend on where she could have gone because he will never have a way to know that. So now, he's like, okay, she is somewhere, I don't know. So my only option is to go to beaucoup or small victory. This game is sequential, but Tom only has 2 strategies. Okay? So now Rosia has 2 strategies. Tom has 2 strategies. Well, it looks like as if the game was simultaneous. They play sequentially, but since there is no information that is improving between the 2 turns, it is as if they decided to go to choose to go to a place at the same time. So what's interesting with this diagram or this dendrogram is whether the game is sequential or simultaneous the game is exactly the same. The normal form game will be exactly the same as well, because Tom only has 2 options, Russia has 2 options. Well, by options I mean strategies, sorry. And we are back to the original simultaneous move game. This is particularly important because if you remember the definition of a subgame, the second part of the definition was saying that a subgame does not cut an information set. So this is not a subgame anymore because it is cutting the information set. The idea is that this is not a subgame because Tom does not know if Russia went to small victory or not. So he cannot consider each case separately. In this case, since this and this are not subgames, the only subgame we have is the game itself. And so, just by changing the structure of information, we went from 3 subgames to only 1 subgame. Now, let's go through repeated games that are played finitely many times. So imagine the following stage game. 2 firms produce the same good and they set prices. So it's a kind of a Bertrand competition, if you like. Okay. So here the options are they can either set a low price or set a high price. So it's not exactly a Bertrand competition, okay? Just to make things simple here. So if both firms charge a low price, then profits are going to be 5 for each firm. If both firms charge a high price, profits are higher, they collude, and profits are equal to 15 for each. Now, if one firm charges a low price, but firm 2 charges a high price, then firm 2 is not getting any customers, so its profit is 0, and firm 1 gets a profit of 25, and vice versa. We have gone through this game in the first game theory lectures, so by now you should be familiar, and you should know how to find the Nash equilibrium. How many are there? 1. It is in dominant strategies. Setting a high price is never a best response. If the other firm sets a high price, sure, firm 1 could set a high price as well and make a profit of 15, but it could also set a low price to make a profit of 25. So if one firm cooperates, the other one wants to default. If one firm defaults, the other one doesn't want to cooperate. So at the end of the day, the Nash equilibrium will be at this cell where low price is played by both firms. Now imagine that these firms are competing in prices every day. In fact, this is what they do on a daily basis. Sometimes prices don't change over the course of several months, but sometimes prices change rather fast because there could be changes in the demand and so on. Now, imagine that once they play the game once, so today they decide low price or high price, then tonight they will see what the other player did, because at the end of the day they will both get their payoff. So they will know what the other firm did. It means that they can use today's play and today's result, today's outcome, to decide what to do tomorrow. Now, strategies again have to depend on the past. So, one more time, they are going to be tedious to write down. Imagine firm 1, for instance. Well, if they play the game twice, then firm 1 has to choose what to do in the first period, and then what to do in the second period. But in the second period, firm 1 has to base its actions on what was done the day before. So, for instance, in period 1, it could decide to play low price, but then in the second period, it could play high price if low price was played before, or it could play low price if low price, high price was played before, or it could play high price if high price was played before, and so on. So, in the second period, each action will depend on what happened before. Now, how many things could have happened in the first period? In the first period, what could have happened was low price, low price, high price, low price, and high price, high price. So there are 4 possible outcomes here at the end of the first day. The second day then, the action of, or the strategy of each firm needs to include an action for each possible outcome from the day before. And again, very tedious. Of course, a strategy that says low price regardless is also a strategy because it lists what is going to be played in each possible history. If this is played, low price. If this is played, low price. If that is played, low price as well. Low price regardless. Now, if the game has a unique Nash equilibrium, we can use backward induction, and that's going to get us the solution rather fast. Because remember, if you want to find the subgame perfect Nash equilibrium, you need a Nash equilibrium to be played in each subgame of the game. Now, think about the second day, so the last day the game is played. Well, what is the game played the last day? The game played is pretty much this game, because it's a simultaneous move game. So it's the same as having a tree with this kind of information set. They played this the last day. And since we know that there is only one Nash equilibrium, then in any subgame perfect Nash equilibrium, at least low price should be played the last day. That's the minimum requirement. Anything else played the last day would not be a Nash equilibrium, so it cannot be a SPNE. So subgame perfection means that the unique Nash equilibrium will be played the second day. But given that this is what's going to be played the last day, what is the best response in the first period? Well, the unique Nash equilibrium in the first period is also to play low price. So what's going to happen here is low price, the stage game Nash equilibrium will be played every period. And this is actually a theorem. In a finitely repeated game, if the stage game, so the game played every period, has only one Nash equilibrium, the unique subgame perfect Nash equilibrium is to play the Nash equilibrium in every period. In this example, if you have to write down the Nash equilibrium, that would be low price regardless, low price regardless, because they both play low price no matter what happened before. Or you could write it as low price regardless for firm 1, and for firm 2, low price in the first period, low price regardless in the second period. That would also be valid. Now, if there are other equilibria, there is more than one Nash equilibrium in the stage game. Imagine the battle of the sexes. we saw that in the stage game, when it's simultaneous moves game, we have 3 Nash equilibria. 2 of them in pure strategies, the ones where they meet, and 1 which is a mixed strategy Nash equilibrium, where they go to a place with a certain probability and to another one with the complement probability. In this case, well, it means that the last day, if they play the Battle of the Sexes the last day, we have 3 possible Nash equilibria. And given this Nash equilibria, then we have to think about what they could play in the first period. So the set of SPNE would grow very, very quickly. What we know with this theorem is that if there is 1 Nash equilibrium in the stage game, then there is only 1 sub-game perfect Nash equilibrium. It is a very powerful result. Any questions so far? This is the easy case. If I give you an exercise where there is 1 Nash equilibrium in the stage game, and I tell you, well, what if this game is played 10 times, 20 times, 1 billion times? Same thing. The only sub-game perfect Nash equilibrium will involve playing the Nash equilibrium at each stage game. Even if it's a billion, because a billion is big but finite. Now, the more interesting case is if they play infinitely many times, or if players do not know when they will stop playing this game. So, super games. So suppose the same game as before is played over and over for as long as the world exists. So, if players play low price in each period, we still have a sub-game perfect Nash equilibrium, same as before, no problem with that, but it's not the only one anymore. We might find something actually more interesting. And let's consider a particular strategy called a Grimm trigger strategy. The Grimm trigger strategy says you set high price until you see your rival set low price. So you're going to propose a high price every period as long as your rival, the other firm, doesn't charge a low price. And this as long as, this until, is going to be the trigger. From then on, if the other firm charges a low price, then it becomes low price forever, or low price regardless. And that's what we call the Grimm strategy. We say it's Grimm because low price, if you remember, is the defect strategy. It's like not confess. It's like confess in the prisoner's dilemma. So it is the non-cooperative strategy. High price is the cooperative strategy. It corresponds to being nice to your opponent. So the strategy is saying that I am nice with you as long as you're nice with me. As soon as you're mean to me, as soon as you as soon as you charge a low price, that's my trigger. Okay, then I'm going to play low price as well, and I'm going to play forever. So the low price is going to be the Grimm trigger. It's going to be the punishment. You screwed me over once, I'm going to screw you over forever then. No forgiveness. Note that this strategy, again, specified what is being played in every case. It says, start with high price the first day, so you got to start somewhere, And then it says, continue to play high price in every history where the other opponent plays high price as well. As soon as you see a low price, then you play low price regardless. So again, it is specifying what is going to be played for each possible history of the past. And every time you define a strategy with sequential games and repeated games, make sure that you specify all the possible moves for all the possible histories. So imagine that firm 1 uses a Grim trigger strategy. What is firm 2's best response? Well, let's think about it. Once firm 2 sets a low price, then because firm 1 is going to reply with low price forever, that's what the Grim trigger strategy is saying, then firm 2 should stick to low price forever, right? So as soon as low price is played by firm 2, it should be low price forever by firm 2. That's the best response. That's a part of the best response. But does it ever pay to play low price in some period? So is it advantageous to at some point play low price, knowing that the Grim trigger strategy of firm 1 means that low price will be played forever? Suppose firm 2 plays high price forever. That's one possible strategy. It's high price regardless. Firm 1, again, is playing Grim trigger. So, Grim trigger says, I play high price as long as you play high price. Well, if firm 2 is playing high price forever, then firm 1, playing Grim trigger, will play high price forever. So both will play high price forever, and firm 2 will get the payoff of playing high price every day for the rest of its life. Now, when players are considering, firms are considering their strategies, they are considering them today. They have to think about the money they're going to make tomorrow, and the day after tomorrow, and a week from now, and a year from now, and 10 years from now. However, the money made 10 years from now is not worth the same as the money made today. So we need to discount the payoffs that are going to happen later because they are not valued as much. The idea is, do you prefer me to give you $100 today or $100 in 2 years? What do you prefer? I think by now, all of you will have answered, you prefer to receive $100 today. For two reasons. First of all, inflation usually is positive and is such that with $100 in 2 years, you will be able to buy less things than with $100 today. Correct? That's the first thing. The second is, if I give you $100 today, you can save this money and 2 years from now, get $100, your original amount, plus some interest. So $100 given to you today is not the same as $100 given to you 2 years from now. $100 today is worth the same as, let's say, $110 in 2 years, if the interest rate over 2 years is 10%. Then you will be indifferent. Give me 100 today or 110 in 2 years, same thing, same value. So we need to discount the money made later because they're not valued as highly as the payoffs made today. This is why we use this discount factor, delta. So if Firm 1 plays Grim Trigger, and Firm 2 plays High Price Forever. Firm 2 is playing High Price, so both firms will end up playing High Price. Firm 2 gets $15 today, that's the profits of 15, and then it's going to get 15 tomorrow, the day after tomorrow, and so on. But because tomorrow doesn't matter as much as today, we are going to discount tomorrow's payoff by an amount delta. And the amount delta is between 0 and 1. Which means that $15 today is the same as $14 tomorrow, something smaller. Because again, overnight, I could save this money and get some interest. But what about 2 days from now? Well, 2 days from now, I could save my money for 2 days and get even more interest. So, 2 days from now is going to matter even less than tomorrow, which matters less than today. So, if tomorrow gets a discount factor delta, then 2 days from now we'll get a discount factor delta squared. And then 3 days from now, or 3 periods from now, delta 3. And since delta is between 0 and 1, when you elevate to the power of 2 and then 3 and so on, the number in front of 15 will get lower and lower. It's the same as me asking you, do you think more about what you're going to eat today or what you're going to eat a month from now? Well, probably you're trying to secure what you're going to eat today first, because if you don't eat today or for a week, you are going to starve and, well, you might die eventually, or at least you might get into health problems. Now, since it is forever, then this sum is going to go forever. Delta 4, 15, delta 5, 15, and so on and so forth. Well, if you factorize by 15, so you put 15 in front, then in the brackets you end up with 1, which is here, plus delta square, plus delta cubed, plus delta 4, and so on. This sum is infinite. It goes forever. Now, there is a mathematical formula that you need to know, is that if you sum those terms infinitely many times and delta is between 0 and 1, that's a very important condition, then this infinite sum doesn't go to infinity. It's going to stop eventually. It's going to converge. And it's going to converge to 1 over 1 minus delta. The idea is that, imagine delta is equal to 0.5. You have 1 plus 0.5 plus 0.5 squared. 0.5 squared is 0.25. So you have 1 plus 0.5 plus 0.25 plus 0.5 to the power of 3, which is even smaller. So you add infinitely many terms, but each new term is lower than the previous one. And so eventually you're going to get to delta to the power of infinity, which is 0. 0.5 to the power of a billion is going to be 0.000000, and I don't know how many zeros. So that eventually this infinite sum will converge, will get closer and closer to this number. If delta is 0.5, this number is equal to 1 over 1 minus 0.5, or 1 over 0.5, and 1 over 0.5 is equal to 2. So this is the present value, of the payoffs for firm 2 if firm 2 plays high price forever when firm 1 plays grim trigger strategy. Now we need to compare this strategy, high price forever, with other strategies. Another strategy could be high price, low price, high price, low price, high price, low price. Alternate. Doesn't matter the history. That could be a strategy. Another strategy could be low price forever. Again, it specifies what is going to be played for each possible history. So let's compare this strategy, high price forever, with a couple more. So now suppose that firm 2 plays low price. If firm 2 plays low price, then firm 1 is going to retaliate. That's the trigger part. And it's going to play low price forever, starting the next period. So firm 2 is going to make $25 today. Why 25? Because firm 2 is playing low price, and firm 1, by Grim trigger, is playing high price. That's what the strategy says the first day. So firm 2 makes a good amount of money the first day, but then at the end of the day, firm 1 sees that firm 2 played low price, and so firm 1 is like, oh, okay, low price forever. And then starting tomorrow, firm 1 will play low price. That's what Grim trigger says. And firm 2, as we saw before, should keep playing low price. So after that, firm 2 will make a payoff of 5 forever. This is the low price payoff. Again, gathering all the discount factors, note that here, I do not start with 5, I start with 5 delta. Because the payoff of 5 starts only tomorrow. Today, we have the nice payoff of 25. So we need to make 1 plus delta and so on appear to use the formula. However, we start with delta. So we can factorize by 5 and by delta to get, in brackets, 1 plus delta plus blah blah blah. Now, this number here is equal to 1 over 1 minus delta. So the final discounted value of this strategy is going to be 25 coming from today's big payoff plus delta times 1 over 1 minus delta times 5. That comes from firm 1 punishing firm 2 by playing low price forever. Now, we are going to compare whether setting high price forever is better than deviating and setting low price. So, for firm 2, playing high price is better than playing low price if this number is bigger than this number. We are comparing payoffs. So, we get this inequality, and then you can play with delta and find that it depends on how big delta is. If delta is bigger than 1/2, then firm 2 prefers to play high price forever as opposed to low price forever. Here is the intuition. Delta discounts the future. So the higher the delta, when delta is high, it means that this payoff tomorrow is close to 5. It's not as big, but it is close. Whereas if delta is small, imagine delta is equal to 0. Well, it means that our firm 2 doesn't care about the future at all. Just doesn't care. Only today's payoff matters. When delta is actually equal to 1, the highest value, then you would end up with 25 plus 5 plus 5 plus 5 forever. Because delta would be equal to 1, so 1 squared is 1, 1 to the power of 3 is 1, and so on. So when delta is big, it means the future is valued. You care. In here, it says that when delta is big enough, so when we care enough about the future, when firm 2 cares enough, Firm 2 prefers to play high price, which is prefers to cooperate. Why? Because as soon as it deviates and plays low price, then it's going to get a small payoff for the rest of its life. Or, in fact, forever. So if firm 2 cares enough about the future, it will fear the punishment. And it will prefer to cooperate. And firm 1, we can make the same argument for firm 1. Assume firm 2 plays Grim Trigger strategy. If firm 1 plays high price forever, it gets the same payoff as before, and so on. Now, we checked if high price was a best response to Grim Trigger. So we said yes, high price is a best response to Grim Trigger if delta is big enough. But now we need to check the other way around. We need to check if Grim Trigger is a best response to high price forever. You can use your intuition. If the other firm plays high price forever, what do you want to do? Do you want to stay nice? Why? You can play low price forever and get 25 every day for the rest of your life and even beyond. So if the other firm is going to play high price forever, playing high price is not a best response. Low price is going to be the best response. So Grim Trigger is not a best response to high price, although high price is a best response to Grim Trigger. So we don't have a Nash equilibrium here. However, if firm 1 plays Grim Trigger, then Grim Trigger is a best response to firm 2. So Grim Trigger is a best response to Grim Trigger, and vice versa. Interestingly, if both firms play Grim Trigger, it means they play high price forever, because they play high price the first day. And Grim Trigger says, if high price was played before, they keep playing high price. And they're going to keep playing high price forever. So, Grim Trigger, again, you play high price the first day, and as long as the opponent keeps playing high price, you keep playing high price. If the opponent plays something else, like low price, then you play low price forever. That's what Grim Trigger strategy is. So, if the other firm is going to be nice forever, with high price forever, then you do not want to play Grim Trigger. You do not want to be nice. Why? You could be mean forever and get 25 every period instead of 15 every period. But Grim Trigger is going to force players to stay nice. Grim Trigger contains the trigger. The trigger is if you cheat or if you play low price, then it's going to be low price for the rest of your life. So you're gonna maybe make a good payoff of 25 today, but tomorrow, for the rest of your life, your payoff will be 5. And this leads us to a very important theorem, a fundamental theorem of game theory, called the Folk theorem. The Folk theorem says that if players are sufficiently patient, so the discount factor is high enough, the cooperative outcome, high price, so both firms being nice to each other in every period will happen, can be supported in an SPNE of the infinitely repeated game. Be careful about the wording here. What's going to happen is they will end up playing high price forever, But high price forever is not the strategy. The strategy is Grim Trigger. But Grim Trigger says play high price as long as the other firm plays high price. So when I say can be supported, what I mean is this is what is going to happen, but high price is not the profile of strategies. This is what is going to be played in the SPNE, but the SPNE, if you have to write it down, is Grim Trigger, Grim Trigger. That's what the SPNE is, not high price forever, high price forever. This is called the Folk theorem because back when game theory was flourishing, around the 60s, 70s, maybe 80s, everybody, all the experts in the field knew this theorem, knew this result, but nobody proved it for a while. So it was commonly known that cooperation would happen if the game is played forever. It was known, but nobody had proved it. And eventually the proof came along. So for a long time, this was called the Folk theorem because it's something that is widespread among the folks of the field, but it's not an actual theorem. And eventually somebody proved it, and that's why they gave it the name Folk theorem. So, being patient means valuing the future, having a high delta. A patient player will avoid getting low payoffs in the future. And this is this fear, the fear of that trigger, that makes players cooperate. And so if players are patient enough, they play cooperatively at the SPNE. But again, the strategy played is going to be Grim Trigger. It's going to be some strategy that includes being nice until somebody is not nice anymore, and then being mean forever. So any type of trigger strategy will be can be an SPNE if players are patient enough. Again, they have to value the future enough. And be careful, many profiles of strategies lead to high price being played forever, but they're not necessarily an SPNE or an NE. Like high price forever, or is a profile of strategies. But as we saw, if one player plays high price forever, the other player wants to play something else. So high price forever is not a Nash equilibrium whatsoever. Grim Trigger is. And both of these profiles lead to the same actions being played. There is another strategy called tit for tat. Tit for tat consists in playing high price first, so being nice first, and then playing whatever the other player did before. That's it. So if both firms play tit for tat, they play high price the first day, and then the next day they're gonna see that each other played high price the first day, so they're gonna play high price again. So on day 2 they're gonna play high price as well, on day 3 as well, and so on and so forth. They will end up playing high price both forever, but the strategy is I play what the other guy did the day before. It turns out that it's a Nash equilibrium, but it is not a subgame perfect Nash equilibrium. How to prove it? I will not show you this here. This is a graduate level result. But just know that tit for tat is a Nash equilibrium, but is not a subgame perfect Nash equilibrium. And, well, the other profile was high price forever, or always high price. But firm 2 always wants to play low price if firm 1 plays high price. So always high price is not a Nash equilibrium at all. So let's talk about cooperation through repetition. Because the game or the relationship is sequential, players can adopt contingent strategies. They can look at what happened in the past and play as a consequence. What they can do then is punish bad behavior. So they look at a history and they say, that player was mean before. So I can punish that by playing a strategy that will give him a low payoff. Or on the other hand, if a player was nice to you, then you can return and play nice the next period. So you can punish bad behavior, but you can also reward good behavior. Now, as we saw in the first part of the lecture, if the game is repeated finitely many times, backward induction rules out punishments and rewards. There is no point in being nice to the other knowing that there is an end to the game. If there is an end to the game, subgame perfection says Nash equilibrium should be played the last period, which in this case is low price. And given that low price will be played eventually, then firms just have an incentive to play low price every period. That's the first result we saw. But if they play either forever or there is no predetermined end to the game, then there is no last period. Live for another day. And so strategies like Grim Trigger are sequentially rational and can sustain cooperation if players are sufficiently patient. If they sufficiently care about the money they're going to make for the rest of their life, the threat of being punished for the rest of their life is a good enough threat for them to cooperate and never deviate. That's what the Folk theorem says. So we need repeated play infinitely many times, and we also need a high discount factor. A firm that only cares about today's payoff, like a hit and run kind of firm who says, I'm only here for a good time, not for a long time, then they come, they play competitive, they play mean, and then they don't care about the future because they can exit the market or something. So if players are patient, it means the future matters. Future punishments are severe in the case of defection, and future rewards in the case of cooperation are going to be valued high. Let's go back to the previous example. So we know that the stage game has a unique Nash equilibrium, and it's in dominant strategies. So this game is a prisoner's dilemma. And now assume the game is played infinitely many times. So let's, again, instead of talking about the intuition, let's solve it using comparing payoffs. Is the profile of strategies always high price, a Nash equilibrium? We saw that it is not the case. If one firm plays high price no matter what, the other firm wants to play low price no matter what to get a huge payoff. Well, always low price always yields a higher payoff. 25 forever is bigger than 15 forever. Now, is the profile of strategies always low price, a Nash equilibrium? If one firm is going to play low price forever, then the other firm doesn't want to play high price. It's going to get screwed. Because playing high price when the other firm plays low price means a payoff of 0. So it's better to also play low price to get 5 forever instead of 0 forever. So always low price is the best response, and always low price is indeed a Nash equilibrium. What about tit for tat? So tit for tat again says high price first, then play what the other played the round before. Now let's compare tit for tat with alternative strategies. And we're going to compare with 3 other strategies. One of them is called always high price. We already know it. The other one is always low price. We already know it. And then there is another one. It's called anti-tit for tat. So it is exactly the opposite of tit for tat. So instead of starting with high price, you start with low price. And instead of playing what the other player did, you play the opposite of what the other player did. Let me tell you, it's going to get messy. But you have to take your time and list all of the payoffs. So, if firm 2 plays always high price and firm 1 sticks to tit for tat, then firm 2 plays high price every period, and tit for tat is going to make firm 1 play high price every period as well. So the discounted payoff will be 15 over 1 minus delta. Now, if firm 2 always pays low price, the first day, firm 1 will play high price. That's what tit for tat says. So on the first day, firm 2 will get a payoff of 25, the highest payoff. And then the day after, firm 1 is going to play low price because tit for tat says play what firm 2 did before. Firm 2 is playing low price no matter what. So on day 2, firm 1 plays low price, firm 2 plays low price. They both get 5. And then on period 3, firm 1 again is looking at what firm 2 did before. That was low price. So firm 1 does low price. And so they're going to play low price forever. So the present value, the discounted payoffs of firm 2 will be 25 first day and 5 for the rest of its life. Now, if they both play tit for tat, then they play high price the first day. Then the next day, they see that they each played high price. So they play high price again. And they end up playing high price forever. So the discounted payoff here is as high as always high price and tit for tat. The last one is going to be the tricky one. And I strongly encourage you to go at home and to list all the possible situations to obtain this kind of fancy discounted payoff. Let's start with the first day. The first day, firm 1 is going to play high price. Firm 2, playing anti-tit for tat, is going to play low price. So the first day, firm 2 is going to make a payoff of 25. Okay. Then the second day, firm 1 is going to imitate what firm 2 did. So on the second day, firm 1 is going to play low price. And firm 2 is going to play the opposite of what firm 1 did before. Firm 1 started with high price. So firm 2 in the second period is going to play low price. So the first day, firm 2 gets 25. On the second day, both firms play low price. So firm 2 gets 5. Then on the third day, it's going to get messy. On the third day, then, firm 1 plays low price because it imitates firm 2. But firm 2 does the opposite of what firm 1 did. Firm 1 played low price, so firm 2 will play high price. So the third day, firm 2 will make a payoff of 0. On the fourth day, I think I'm going to stop after the fourth day because it's getting tricky. Very hard to just think about it without writing things down. On the fourth day, firm 1 will play high price, and firm 2 will play high price as well. So on the fourth day, firm 2 will make a payoff of 15. And so on and so forth. So what you need to do is list what's going to happen each day. Don't forget to put delta there. And eventually you will catch a pattern. It's going to be cyclical. Every 3 days, the payoff will be 25. Every 3 days is going to be 5. And every 3 or 4 days is going to be 15. And so eventually you can gather the deltas together and you will be able to obtain this formula. I strongly suggest you to try it and then come to office hours to talk about it. So, now, remember, we want to check if tit for tat is the best response to tit for tat. So we want to check if this payoff is higher than all the other payoffs. We know it's already the same as the first one, but now we need to know for what value of delta it's going to be better than this one and than this one. Well, if you want to solve the equation that involves delta to the power of 4 and delta to the power of 3, good luck. I just tried delta bigger than 0.6. So I tried 0.8 for instance, and it was working. So I use a calculator, I use software to solve the equation, and 0.6 was the threshold. In this case, this payoff is the highest of all. So tit for tat is the best response to tit for tat. And so you can go the other way around. If firm 2 plays tit for tat, then if firm 1 is patient enough, firm 1 also wants to play tit for tat. Note, by the way, that we are checking Nash equilibrium here. We're not checking subgames. Since the game goes forever, how do you make a subgame? There's always a smaller subgame you can find, right? So making a tree and finding subgames that grow infinitely will not help you much. And one can show that tit for tat is a Nash equilibrium, but is not a subgame perfect Nash equilibrium using what we call the one-stage deviation principle. Don't worry about it. It won't be covered in this class. It is not easy. It is a graduate level concept, but just to remind you that a subgame perfect Nash equilibrium is a Nash equilibrium, but not all the Nash equilibria are subgame perfect. And tit for tat is one such example. Note as well that here I assume that delta is the discount factor for both firms. Both firms have the same discount factor. In reality, one player could have a discount factor of 0.5 and another player could have a discount factor of 0.9. Why not? So you also have to be careful about how each player values the future. Now, let's look at the same game, but I changed one payoff. Instead of 25 here and here, I put 55. So when firm 2 plays high price, but firm 1 plays low price, then firm 1 gets a higher payoff than before, and vice versa. let's do the same computations as before. Look for delta such that Grim trigger is a Nash equilibrium. So we assume firm 1 plays Grim trigger and compare, for firm 2, compare different strategies and hopefully Grim trigger, or look for delta such that Grim trigger is the best response. So in principle, we should compare Grim trigger to all possible other strategies, but there is an infinite amount of them. What we know, however, is that whenever firm 2 plays low price, firm 2 should play low price for the rest of its life and beyond. So at least once low price is played once, we know that the best response will be to play low price forever after. So that is going to rule out many strategies that we don't even need to look at. So if they both play Grim trigger, well, they both play high price forever, and the payoff is 15 over 1 minus delta. If firm 2 plays always low price against Grim trigger, it will get 55 today, big payoff the first day, but then eternal punishment. So the first payoff is higher than the second if delta is bigger than 4 over 5, 0.8. Do you remember the number we found before when the payoff wasn't 55, but it was 25? The delta was 0.5. So the payoff that changed is the cheating payoff, the one that a firm can get by playing low price when the other one plays high price. So since the payoff by cheating today is higher than before, the player, the firm, needs to be more patient, needs to care more about the future to cooperate. Otherwise, it says, the payoff today is way too good. I don't care about eternal punishment because of the money I can make today. So, if the cheating payoff is higher, players need to be more patient, they need to care more about the future if you want cooperation to be sustained. Note, by the way, that using this one-stage deviation principle concept, we can show that Grim trigger is a subgame perfect Nash equilibrium. And cooperation is sustained as per the Folk theorem. That's it for this lecture on repeated games. Have a good rest of your week and see you in the next one. Bye.